We're going to work further in this lesson with interpreting our sinusoidal functions. And remember, our sinusoidal functions are these nice, smooth, wavy curves. So I want you to take a few minutes right now to complete this table. You might look back in your notes to remember what each of these things means. And then after you've completed the table, come back to the video and check and see how you did with it. All right, so hopefully your answers are matching up with mine. I've highlighted just one cycle for each of those particular sinusoidal curves. And if I've made any mistakes or you disagree with anything, send me an email, let me know, just in case. Hopefully we are good though. All right, let's interpret some sinusoidal functions here. So I have this first example. In high winds, the top of a flagpole sways back and forth. It kind of vibrates up there. The distance of the top of the pole, the tip of the pole, vibrates to the left and to the right of its resting position, and it can be defined by the function I've given you, where d at t is the distance in centimeters and t is the time in seconds. So here's the first function, and I should actually underline that one in red because it is represented by the graph I have in red below. Now, if the wind speed decreases, the motion of the tip of the pole can be modeled by this new function, which is the blue one that I have below. And you can see those equations are very similar. Really, the only difference here is the second one has a 1.5 where the first one had a 2. So using graphing technology in degree mode, so if you're in Desmos, you've got to go to the little wrench in the corner, the top right corner of your screen, and make sure you change into degree mode. By default, it's in radian measure. So if you're using this and trying it on Desmos, which you will be working with Desmos later for future lessons, you want to make sure you change over to degree mode. So you're going to graph the two functions and discuss the implications of the reduced wind speed on the flagpole. Refer to the period, axes, I left a comma out of there, axis and amplitude of each graph. So if we look at the original red graph here, I'm noticing the axis is at y equals 0 or d at t equals 0. So the actual t-axis here is the axis of the curve. Now, if you had a still day, there was no wind at all, that flagpole is just going to be a nice vertical flagpole to the ground, and there's not going to be any vibration happening there. So here's my little flag coming off of that flagpole. However, when you have the wind, it's going to make this oscillate back and forth in that wind, vibrate back and forth. And usually when we go to the left, that's a negative value, and when we go to the right, that's a positive value if you think of your x-axis. So what the axis of the curve here represents is if there was no wind at all, that would be the straight up and down of the pole. However, the wind comes along and it's going to push it to the right by 2 centimeters. And then it gets as far as it is going to go, and then it comes back to the center resting position, but then it sways to the left by 2 centimeters and back to the center again. So that's really the flagpole heading off 2 centimeters to the right. So originally, dot, 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 here's your original flagpole. It heads 2 centimeters to the right, it comes back to center, goes 2 centimeters to the left, and then back to center again. So that's the flagpole oscillating back and forth in the wind. When we look at the period is 0.5. So it takes a total of 0.5 seconds to move from the right, or from the center to the right, back to the center to the left, and back to the center again. So in half of a second, it takes half of a second to go for that vibration, that one cycle of vibration to happen there. That's true even if the wind decreases in speed, because if you look at the blue function, it also has that period. So it's still taking half a second for it to complete its vibration. The difference when the wind slows down is how far to the left and the right it goes. So the amplitude decreased to only 1.5 in the blue graph versus the 2 in the original graph. So it's only going 1.5 to the left and to the right of the center. So it's not vibrating quite as far to the left and right. So hopefully that's making sense. The axes is just no matter whether you're the blue graph or the red graph, the straight up and down will always be your straight up and down. The axis is your normal position without that vibration to the left or to the right. So I've just summarized there the things that we were talking about in terms of those characteristics. All right, on our next example, we have an amusement park where a math teacher had different students ride 2 different Ferris wheels. Sounds like a fun math teacher. A teacher collected the data and produced 2 graphs. So here's where, this actually came from your textbook, so you can refer to page 344 in your textbook if you want to get a better look at these graphs. Complete the chart for the 2 graphs, so take a moment and fill these things in and see if you can answer the questions that go with this. All right, so we should have, for the first one, your amplitude is 6. The equation of the axis is at 7. So if you look at here, y equals 7, dot that across. Our distance here is 6 units from here to here. And it takes 40 seconds to complete 1 cycle. So 1 cycle spans that amount of time. Likewise, this also had a cycle length of 40 seconds. But its equation of the axis is now down here at 4, and our amplitude, the distance from here to here, was 3 units because we went to a max of 7 and a min of 1. So 3 units above and below that y equals, or that should be h equals 4, not t. All right, so I'll fix those up, and then amplitude, we can talk about what that means for characteristics here. So the amplitude is that distance from that middle point. So the middle point, remember, for a Ferris wheel or any rotational device would be where the center of the turning is happening. So the axle of the wheel, axis or axle of the wheel. From there, our amplitude was 6, so the amplitude tells us the radius of our Ferris wheel. So the first one has a radius of 6 meters, and the second one has a radius of only 3 meters here. So our second wheel is definitely smaller than our first wheel. All right, the next thing we need to talk about here is, oh dear, is the equation of the axis. And if we talk about the equation of the axis, again, that's where the center of the wheel is. For Ferris wheel A, that axis is 7 meters above the ground, whereas for Ferris wheel B, that axis is only 4 meters above the ground. The period is the same for both. For both, it takes 40 seconds for that wheel to make 1 complete rotation. So that means if you're sitting on Ferris wheel A, you're covering a lot more distance in the exact same amount of time as Ferris wheel B. That means you're riding, you're going a lot faster as you turn. You're going to feel like you're flying a lot more quickly around that wheel than on Ferris wheel B. So compare the 2 Ferris wheels. Definitely A is bigger than Ferris wheel B. B will seem way slower than Ferris wheel A because you're traveling less distance on Ferris wheel B, but in the exact same amount of time. All right, in this last example here, a car tire has a diameter of 106 centimeters. So if I think of my tire, it's round. Draw a nice round tire here. Get the correct tool. Its diameter is 106 centimeters, so I could draw the diameter across, up and down. It doesn't matter as long as it's kind of looking like it's going through the center. 106 centimeters there. At a particular speed, it makes 1 rotation every 2 seconds. So if your complete cycle is 2 seconds, you should have 1 complete sinusoidal curve for that. The tire picks up a stone as it rotates. Sketch the graph representing the height of the stone compared to time for 2 rotations of the tire. All right, so I'm going to put time as my independent variable here, and the height of my stone is going to go here. Now, to be picked up off the ground, your height would be 0 at that moment. And as the wheel turns, a quarter of a turn, you're going to be parallel with the center of the wheel. And then at a half turn, that stone will be at the high point. then you're back at the center of the wheel, which is your axis of your curve, and then you're going to go back to your minimum point. That whole rotation is going to take us 2 seconds. So at 1 second, at half of a rotation, it should be at its maximum, and at 2 seconds, so let's make this 2 right here, 2 seconds, it's back down on the ground again. And at 1 second, it's going to be up here at its maximum. Now the maximum height would be the 106 centimeters. That's going to go here. Half of that amount would be 53. So 53 is halfway. And at half of a second, that stone should be, so here's 1 second. And I could do this on grid paper, but I don't have grid paper here. I'm sure there's a way to put it in, but I just don't know how to do that. And then also it's halfway between 1 second and 2 seconds. It is halfway or parallel to the axis of the curve. So if I actually join these together in a nice smooth curve, stone goes up parallel to the center of the tire, gets to the peak or the top of the tire, back to the center of the tire, back to the ground, and then it repeats itself. So let's make another cycle here. 3 seconds, 4 seconds, back on the ground, oops, wrong color, back on the ground. Here we should be at the maximum. Here we're going to be on the axis of the curve, here and here. So we can draw another cycle for a second rotation. So hopefully that makes sense, which pulling pieces together and understanding how these are actually used to model real life situations.